is a security. Okay. So we were talking about random Sundar models. Uh, so these have non-factorizable geometry given by some such factors which sits in front, which is a conformal factor. Okay, this is a conformal factor in the metric. So these are not, they are inspired by curved spaces, essentially have curved like geometries. Um, I'm going to put few more things in the Teams page if you want to know. There is an inspiration from M theory to this kind of setup. Essentially, we have a setup in which we have two brains at phi x is equal to 0 and x is equal, y is equal to 0 and y is equal to phi r, or phi is equal to 0, phi is equal to pi, and each one of them is called something. This is called an IR brain, or this is the visible brain, this is the IR brains, I'm sorry, sometimes called also IR brain. This is called UV brain, and this is called hidden brain. And there is a huge negative cosmological constant inside in the bulk essentially. And there are these two boundaries in which you have x mu sitting on both sides. And so the extra dimension is span, okay. At each x mu you have an extra dimension, okay, which is sort of, it's a line essentially. At a line essentially, the extra x mu is separated by an extra dimension as in a line, and the boundary conditions on this side are different than the boundary conditions on. So only one x mu has the standard model fields, which we call the visible brain, which is the standard model. So this S1 by Z2 seems to have been inspired by, in string theory. I failed to mention it last time. I'm going to put it in the Teams files sector. And if I don't, otherwise just send me an email. I'll share with you all my Dropbox folder essentially, or this folder. Okay. This has some inspiration from M theory construction of Horawa in superstring theory. So Horawa theory is an M theory construction in 11 dimensions. So the 10th dimension resides on two places, and there is an S1 by Z2 in the 11th dimension. The 11th dimension is exactly like compact bidimensional. So this theory is something like 10 times S1 by Z2 within E8 cross E8, and typically there are the string based models in which one of the E8s is called the hidden E8 and the other E8 is called the visible E8. Okay, so you get your standard model from one of the E8s because E8 is an exceptional group. Okay, these are one of the 5 string theories. There are 5 string theories, all of them are connected each other with dualities. E8 by 8, S432, type 2A, type 2B. Okay, and I covered everything, I think. S432, E8 by 8, type 1 string theory. Okay. So there are these 5 string theories, and in between there is an M theory, which seems to have an extra dimension of about 11 dimensions, which is compactified on S1 and C2. So 8 by 8 have been for a long time known as string theories, which give you standard model. Okay, 8 by 8, I don't know, you heard Ashok's lecture, right? Essentially, he also talked about this 8 by 8 essentially. Typically, you take one of the 8s as the hidden sector P8, and the other one you can take it as standard model 8, and you try to get the standard model out of it. The particle representation comes out because it has a large number of vector-like particles, and 8 is a larger group compared to standard model, and typically it leads to SO10 or some granified theory essentially. So there is some inspiration coming from 8 by 8. So a lot of inputs went into the construction of this one essentially. So this is just a construction, ad hoc construction. It satisfies the Einstein's equations. It's a solution to the Einstein's equations, and it's just 5-dimensional. And further, because it's a wrapped construction, and we have seen that it solves the hierarchy problem just with geometry. It's not solving by anything else. It solves the hierarchy problem by putting by the geometry of the warped space-time dimension. And the warping, the dimension is not large. The volume is very, very small, but the geometry is such that it has a large negative cosmological constant, which introduces a warp factor, and this warp factor solves the hierarchy. Now, but then I discussed several problems. Today we will discuss one of the problems essentially. I discussed two main problems. One is this electroequation test, and the other one is this has two brains. Yeah, this has two brains sitting at with a distance r, and this radius r should be fixed to solve the hierarchy problem. So you should not get, because this is a gravitationally attractive force, this potential, meaning you are keeping that in a gravitational field, because only gravity is in the extra dimension. In a gravitational field, will it be stable or not? Meaning, does this R live with the, will be stabilized or will not be subject to gravitational corrections? If there is a tiny gravitational correction, whenever you, what do you mean by stability? That means that if you have small perturbations in gravity, this R should not get modified, because if R gets modified, because it's an attractive force, so it should always, stable means it should always be in the lowest energy configuration, and if it has small perturbation, it should remain there essentially. It should not move to some, it should not fall off or something like that. So this radius should be stable essentially under gravitational corrections essentially. That's the basic idea. Now for that we had to show that it always lies in the lowest energy configuration. Okay. How do you show that this energy system is always lying in the, because it doesn't look like it is stable, because if you put up the brain here, you put up the brain there, so whether the R will get attracted, so R will shrink or R will fall. That is the main issue. So today we will try to address this problem. R not a stable R. Stability of the or essentially the stability of two brains with an opposite tension in a gravitational potential. Okay. And I keep mentioning to you, gravity is an attractive force. The brains with opposite tension should come and collapse with each other, and so this generically you would expect that this thing is not stable essentially. So there is a solution for this stability, and this stability solution goes by the name Goldberger-Weiss mechanism. Weiss is the same Mark Weiss. Isger Weiss, same Weiss. Weiss has so many things in his name essentially. Okay, you know Isger Weiss functions, loop functions. Essentially, you must have heard them. If you heard them, heavy core capital theory or there are these functions called loop functions called Isger Weiss functions. So he's the same Mark Weiss. So this is called Goldberger-Weiss. So what does this mechanism do? To learn this mechanism, let me just say, I have to introduce what are the bulk fields, what is the equation of motion for the bulk fields, and how do you solve them. So this is quite different compared to normal ADD models. Now, again, let's just remember the ADD model. Bulk fields are just causes and sines. Okay, they are just given by sine k by r, nk by r plus cos nk by r. We saw this thing, right? Essentially, that they are 5-dimensional, they are dimension 2, and we say that these just become causes and sines. So they go as these functions, these two causes and sines. So they have profiles. If you want, it will be like this essentially. So their wave function profiles in the extra dimension will be so on. So that they will just repetitive and so on. How do they? Because now one thing we know for sure that in RS they cannot be causes and sines because it's not flat extra dimension. Okay, it's not a flat extra dimension. It is has a warping in it essentially. If it is a pure flat extra dimension and it's just a compactification, you'll have causes and sines because it is just like a simple harmonic motion, and so you will think that you will get a causes and sines. But because it's not, or the space-time is not like a simple circle, it is some sort of a funnel. It's like a wrap in the extra dimension. Okay, it's like a funnel. So you don't expect them to be causes and sines. So what should they be? So to do that, let's just start this. Look at the action. So let's just take a simple scalar field with no interactions. Okay, this is just the Klein-Gordon action. This is the Klein-Gordon free Klein-Gordon field theory. Okay, I am putting it in the action of a 5-dimensional field. Now, typically we use, because everything appears as a function of k, because we can, the mass terms also, we can just take it as some ak square. So A is dimensionless, one parameter essentially. A is a dimensionless parameter which tells you the relation between k. K we say we exactly the same thing, watt factor. K is the watt factor. We just re-express the mass term, bulk mass terms, always in terms of the watt factor. Okay, because we want to say how much it is with respect to the watt factor. The basic idea is essentially that if you consider an effective field theory, even RS as an effective field theory, these mass terms cannot be more than the Planck mass scale. Cannot be more than the Planck scale. So they cannot be very, very large compared to K. So you cannot take 10K, say for example. So then they don't, if RS is an effective theory coming from string theory, we don't know, we have not completely shown it. Imagine that if it is a string theory, you cannot have trans-Planckian masses or something. Okay, it's always useful to see, because the bulk is completely, anything in the bulk should be of the order of the watt factor. Okay, with respect to the watt factor, how much is the bulk mass term essentially is that I wanted to use this because we'll use this for the fermions also, and now how we see RS as a theory of flavor, I'll tell you essentially maybe in the next class or something essentially, yeah. Or perhaps this class itself, but as we'll see soon actually. So this is the basic idea, that you use the bulk masses, always bulk masses, even for fermions or for scalars, always write them in terms of some coefficient times the K, the bulk, okay, watt factor. Now I want to do the KK decomposition. This phi stands for this phi essentially. This is a bulk scalar field. This is the profile of the. So this is your KK mode, and this is your profile. Profile means, that means how the wave function of this particular particle is in the extra dimension. So I just did a factorization. I said it's a non-factorizable geometry, but I am insisting that the functions of this geometry are factorizable. Essentially, I am just saying that you can write them as variable separables. No, I am just writing it as x, a variable, a function for x and a function for y. Okay. Now, the basic idea is that if you integrate over y, after integrating over y, you should get an effective action, and the form of the effective action should be some sort like a equation of motion for the Klein-Button field essentially, with all the modes and everything. Okay, after integrating, what I should get is, after integrating over y, I should get an effective action which will be just 4-dimensional of all the modes and Mn is the masses of these modes. Mn is the masses of these modes. So I will determine what are these Mn's. I have to determine what these F's are. So I have to get all these functions essentially. So this is an effective action. This is an effective action of all the modes after integrating over y. This is important that I am integrating over y essentially. Okay, that's my effective action. That's what I am looking at essentially. So let me write down these profiles f. Now this is whatever I'm going to do is just like quantum mechanics. It's exactly like quantum mechanics. I assume these functions. I write an equation of motion for these functions. I impose orthonormality relations. Okay. It's exactly like quantum mechanics now. So these functions f of n will satisfy putting back this expansion, putting back into the action and deriving the equation of motion. The equation of motion in the y direction would be essentially I'll get an equation of motion. Okay, I get an equation of motion, and this equation of motion will be equivalent to an mn square, which I wrote down in the effective action, times exponential of this. Essentially, you'll end up having this kind of an equation of motion. And then there will be an orthonormality condition because these functions f of I only reside between 0 and pi r. They reside only between 0 and pi r. So between 0 and pi r with these boundaries, they should be orthonormal. They should be orthonormal. Yeah, should erase this one. Okay. So the orthonormal conditions, you can write them as 1 by pi r dy e power minus 2ky pi star of y n f by m of y is equal to delta n. And f tilde is equal to e power sigma y f phi. And so if I just define, absorb this e power k sigma of y, okay, e power k of y to then I'll get canonical, you can canonically normalize these things. So in terms of f tilde, these orthonormal relations are nothing but integral dy f tilde of n over y f tilde of m over y having the phi is equal to delta n. Now, when you expand this action, you end up having boundary terms with on the delta functions, right? And near the delta functions, you have to choose some boundary terms. Essentially, you have to choose either either the derivatives vanish at the boundaries or the fields vanish essentially. Okay, so you have two choices, boundary conditions. Now you will see the problems with this choose essentially. So at the boundaries, you'll have this kind of terms, right? For example, phi n of star f phi n of y. So you have these cross terms, delta terms, which will multiply something like phi n of x del y of phi of y. So at the boundaries, you have actions, you have terms of this type because, okay, which are a combination of the delta functions plus this term. Now you can choose either these functions to vanish or the derivatives of these functions to vanish. If the functions vanish, they are called Dirichlet boundary conditions. If the it's like in electromagnetic theory, what we study. And if the derivatives vanish, they are called Neumann boundary conditions. Okay, so you can either choose such that these kind of terms of the times, boundary terms, you can derive these boundary terms. Actually, you don't even need to use this. Okay, there is another technique. Without using the Keka decomposition, you can actually use the 5-dimensional fields itself and just play with these boundary conditions and get the same equations of motion, essentially same things completely in terms of the 5. Okay, okay, you can. I don't. It's called fermion on an interval and so on. So there are these techniques we can directly use 5-dimensional fields instead of decomposing them into 4-dimensional and 5. So you may have a question, oh, if I use the 5-dimensional fields, you are decomposing it, so what is it? And you may question, this is not a good technique and everything because it's non-factorizable geometry and all kinds of stuff. No, you can actually have orthonormal functions on this interval. Okay, so there are for 5-dimensional techniques, I can suggest you a paper by I think it's called Fermions on an Interval by Shaki, Grosjean, Falkowski and company. It's called Fermions on an Interval essentially. Okay, so the boundary conditions phi r is equal to 0. This is Neumann boundary conditions, or you can directly have Dirichlet boundary conditions. At 0, phi r is equal to 0 is called Dirichlet boundary conditions. Sometimes they are called NN boundary conditions, sometimes they are called DD, because some people, you can also have something called ND, DN kind of things also. At one boundary you give Neumann and another boundary you can have Dirichlet. So you can have mixed boundary condition scenarios also. Okay, so so the solutions depend upon what boundary conditions you use. But the boundary terms will vanish. Essentially the basic idea is that you set the boundary constant to 0. So to summarize up to so far, essentially, let's just follow this method. Okay, we can worry about the 5-dimensional methods later on. So this method, if you follow, the basic idea is that you just again decompose, right? Take the action in 5 dimensions, decompose it into wave functions. But here, I don't know what these wave functions are. I cannot just write e power I k n r. Okay, earlier for ADD models, I just wrote it as e power n k r and then substituted it and everything. I got causes and sines and everything essentially. But here I cannot do that, so I assume some functions. I don't know what these functions are. I say that these are orthonormal because they should be quantum mechanical essentially. So there should be Hermitian, orthonormal, all these kind of conditions I impose. So, and then I write down the equation of motion. After writing the equation of motion, I impose the orthonormality conditions. After imposing the orthonormality conditions, I choose my boundary conditions essentially. Okay, I choose my boundary conditions so that I get my modes essentially. So what you'll end is, of doing all that, the first thing which we need is what we call as a zero mode. But the problem with zero mode, but there is a problem with zero mode. So here I am assuming that the boundary terms vanish. If I assume the boundary terms vanish, I won't have a proper zero mode. The zero mode is not localized essentially. Okay. So the general solution, I assume, again I can just take a general solution in terms of a e power I k of x essentially, and plus b e power I k of x essentially. Okay, and then determine what these k's are or the coefficients are, and so I can try to solve it, because just like any, it's some wave sort of thing, the zero mode. So we want, when mn is equal to 0, without a boundary localized term, the zero mode is delocalized. Why it's a problem? Why it's a problem? The setup of the RS, the setup of RS is such that you should have all the standard model fields only on IR. They cannot be all over the space.
On the boundary.
They have to be on the boundary. Okay, so they have to be on the boundary. Now, if we have wave and we want to identify our zero modes with the standard model fields, like in ADD models and everything, we want to identify our zero modes with the standard model fields. So if this zero mode wave function is completely delocalized, it means that you're essentially putting it up. It won't. You cannot connect it with reality essentially, or the setup is not completely satisfied essentially. So because as if I take a solution at phi of 0 of y, it has a general, because the differential equation will have a solution which is minus 2 root of 4 plus a ky. A is this term, mn will have m square, the bulk mass term, the coefficient of the bulk mass term essentially, plus c2 e power 2 plus root 4 plus a ky. Now C1 and C2 are arbitrary constants, okay, they are arbitrary constants. It doesn't satisfy either the Dirichlet boundary condition nor the Neumann boundary condition at y is equal to 0 or y is equal to pi r. So it is essentially delocalized. Okay, it's completely delocalized. It's all over the space essentially. So to solve this essentially, what we do is we typically introduce one more boundary term. So the scalar field always has a boundary term. Now this is, you keep this in mind. But when we come to Goldberger wise, we don't care. We'll see that why. Okay, what happens? Okay. D power 4x dy minus root g 2bk delta over y minus delta over y minus pi r pi square. So adding is another mass term localized at the boundaries. Okay, another mass term localized at the boundaries, not in the bulk. You are adding another mass term localized at the boundaries. So that the Neumann boundary conditions, which are derivatives, essentially will look like something like dy by dy, minus bk f0 pi of y is equal to at 0 at pi r is equal to 0. This is Neumann boundary conditions. Now finally you get the solution. After adding this term, putting it back into the equation of motion and using this boundary condition, okay, you get the solution.
B is the
F is,
master.
one second, yeah. F is now localized, but it can be localized both depending upon the sign of B, either at UV or IR. Okay, I'll just write it down. F pi of 0 is equal to root k r phi some xi of phi e power b k y, where xi of phi is equal to square root of 2b minus 1 epsilon to 1 minus b minus 1, and this epsilon is nothing but 2r k pi essentially. Yeah, you are asking some question essentially. So
Asking that B is the master.
B is the localized mass term, not a bulk mass term. B is the localized mass term because I am adding that delta is equal to y, y is equal to 0 and y is equal to pi r.
So we add this term in the action that you defined.
The initial action, the five-dimensional action plus localized mass.
Mass.
This is the same technique we are going to use even for the Goldberger wise. Okay, in the Goldberger wise, but we have interaction. That's the main thing because you want to generate a potential essentially. So to summarize, what we have is just if you take a five-dimensional free field with no interactions, scalar field. Okay, so essentially it's like a Higgs. Okay, essentially Higgs has interactions, but anyway, because they're small interactions. So we take a Higgs-like field, five-dimensional, and you see what are the zero modes of it. You see the zero modes of it, and the zero mode seems to be delocalized. And it won't satisfy either the Dirichlet boundary conditions or Neumann boundary conditions. To satisfy this, you add an additional mass term on both the branes. Okay, an additional mass term on both the branes. So bulk mass term is not sufficient. You need to add a brane mass term, okay, also on both the branes. Then you get a solution which is localized and which is dependent upon the sign of B. If B greater than 0, you get localized in the UV brane. If B greater than 1, you get B greater than 1, you get localized in the IR branes. So the canonically normalized profile F tilde of phi of 0 is equal to root k r phi xi phi, this is xi phi e power b minus 1 ky okay, such that if b greater than 1, you are in IR brane. So essentially you need to choose b is equal to 3 or something, and b less than 1, you sit in the other brane.
So stand one fields will be on UV brain.
So if you want to put a Higgs field, say for example, okay, if you want to put in a Higgs field, you want it in the IR brane, or you can put some fields in the UV brane also by choosing your choice of it. There are several applications, but Higgs is always should be in the. If the Higgs is in the bulk, you start the Higgs not as an just a localized field, but as a bulk field. Okay, if you start Higgs as a bulk field, you want to localize it, you have to choose your brane around greater than 2 actually. This is not this sufficient. Finally, when you do all the calculations and everything, it turns out that it should be greater than 2 to be localized on the IR brane essentially. So this is all about zero modes. What about higher modes? What are the KK modes? KK modes are no longer sines and causes. So KK modes are no longer sines and causes. They are given by Bessel functions. So to write the KK modes, m greater than 1 equal to 1, KK modes, mn not equal to 0. So introduce a new sometimes this is also called the conformal coordinate, but anyway, it's not exactly the conformal coordinate. Mn e power sigma by k. So you introduce a new coordinate, okay? Define. So the equation of motion can be written now in terms of some Zn square d square by dzn square Zn I'll tell you what C is. All this operator is acting on e power minus 2 sigma of y f5 of n. So the solutions of which C is nothing but mn square is there, no? Mn square also I wrote it in terms of C times K essentially. Mn square is essentially. So the solutions of this are f5 of n of y given by some normalization constant e power 2 sigma of y j alpha, so Bessel's function e power sigma of y k and these are Bessel's functions of the first kind, and then will be given by Bessel function of the second kind where alpha is equal to the the bulk mass term essentially. So the mass spectrum roughly goes as n plus 1 by 2 k e power minus pi r cube. So it's slightly uniform. The mass spectrum is not regular. Okay, like in the ADD models, the mass spectrum is regular. So you have n is equal to 0, n is equal to 1, n is equal to 2. So the mass spacing is different. Same here, the the difference between the two mass scales differs by what is the bulk mass parameter, essentially, by the bulk mass parameter. So it's not as regular as in ADD models, actually. Okay, as n changes, it also changes. Okay, as n changes, it also. Okay, so couple of more things. This, I think this is a form of Riccati equation. Okay, there is something called the Riccati equation, or which is a form of some Bernoulli equation, something essentially. Okay, so this equation has solutions which you can write it in this particular fashion, and you can solve it essentially, and then of course this you have to find it on mathematical, the zeros of the basis functions and that order one, and then you can get your, the zeros gives you the mass spectrum, which gives you this particular thing essentially. So what we found is that if you have a just a bulk scalar field, bulk scalar scale on a background like Randall-Sundram like background, the zero mode you can localize it on the IR or UV, wherever you want to localize it, and its solution is just an exponential e power whatever that form is, simple form. Whereas for the higher modes, the KK modes of that theory, they are all mostly localized towards the IR. The solution is essentially they are all localized towards the IR with large couplings. If you consider, they are all mostly localized towards IR with a mass spectrum which is given by this particular fashion. Okay, so now we want to stabilize the radius. Okay, we want to stabilize the radius. So the radius idea is that so the basic idea, okay, up to this point is clear, right? So can I erase everything essentially? And then I'll come to Bulberger-Weiss governance. Now the extra dimension is a variable given in phi, right? Angle, the angle phi, which goes from 0 to pi r. And what we need is that this r, or if you want this r, kr should be fixed to a certain point around 10 to 11, right? That's what we want. Let me call this as some RC. So if this field y is equal to r phi, if this r gets a vacuum expectation value, okay, or this phi is chosen to be, or this r gets a vacuum expectation value such that it gets frozen to some RC phi value. RC phi value gets frozen at RC and phi so that it gets a vacuum expectation value, then it is stabilized. That means it's this R field also should get a vacuum expectation value. Now you treat the extra dimension R also as some field. Okay, so the basic idea is that you get a phi dependent potential. You want to get a phi dependent potential, and this potential gets frozen in phi or in the extra dimension or y if you want, y dependent potential, and this y gets frozen because you are taking them as functions of y, right? Essentially, the y should also get a wave. So the y gets a wave such that it gets frozen at y, r essentially. R is a coordinate, but let's take our radius as a coordinate essentially. That's the basic idea. So there are other proposals, but let's just take this one. There is also cosmological constant and stabilization of moduli. So stabilization of a moduli is a issue in string theory. Okay, in string theory, moduli stabilization is a big problem. It is known, and there are several solutions. What is moduli stabilization? The moduli stabilization is that if you have any compact dimension, that compact dimension should be compact in that gravity space. It should remain fixed to those to that particular value of the compact radius. Now, if you don't get it fixed, what happens is, if you write a potential for it, if you just write a gravitational potential for it, so this leaves, you can write it. The basic idea is that you can write all these extra dimensions as some sort of scalar fields in phi, or these angular variables and so on. So these don't have any potentials. If you don't have a field with no potential, they are not dynamical fields. So they have what is called runaway actions. So they can be localized at infinity. So if you write any interaction terms or something, okay, the modulus will be stabilized at infinity. Okay, they cannot be stabilized at any places. These are called runaway action, runaway fields, essentially, runaway potentials, essentially. Okay, so there have been several ideas in string theory how to stabilize them, and one of the biggest success of KKLT is showing that you have multiple vacua after stabilizing all the vacua. So you heard of this word called KKLT? What is the biggest problem in string theory? So where is the landscape come from? Landscape comes from this, that you have string theory, 4 dimensions, 6 extra dimensions. 6 extra dimensions are compactified. It gives to large number of runaway moduli fields. Okay, depending upon the compactification moduli. What do you call space? What kind of space? You can have Calabi-Yau space, complex spaces, and everything. These things will have large number of runaway vacua. So earlier idea was that if you somehow fix all these vacua, you will get only one vacua in which the model lives. Okay, so people were looking at what is the one possible vacua. So basic idea was that if you somehow fix all the vacua, you will get only one vacua. But it turned out that you can fix all the vacua in type 2B string theory. You can fix all the vacua, and it leads to 10 power 500 vacua, which all of them can lead to standard model, standard model essentially, 10 power 500. So these are called. So you can fix all the vacua by putting fluxes in the extra dimension. Okay, you can fix all of them. So you put fluxes or some interactions in the extra dimension, and it fixes all the vacua essentially. So this is shown by KKLT, and before that by Guko and Witten. Okay. So that is the origin of landscape idea essentially. Why you have landscape and multi-universals and so on. So anyway, so this, yeah. No questions, right? Okay. This is more philosophical rather than physics wise, but let's just see what is this one. So this one is you start with a bulk action, standard bulk action, just like what we wrote right now essentially, that 0 to pi r or minus pi to plus pi, it doesn't matter essentially, root g, capital G or small g, this is the same bulk action we started with, okay? Bulk action, we just started with the scalar field. Okay, now you also add on the hidden brain a localized action this is like mu square h square, mu square time lambda v is essentially mu square, okay? Lambda v is essentially mu square, lambda v square is nothing but mu square, and lambda phi 4 theory. So you essentially write that mu square h square or mu square phi square plus lambda phi 4 theory essentially. So you add this term both at the visible sector brane and hidden sector brane. So there are two lambdas. So the setup essentially now is that you have your RS, okay? This is your visible sector, this is your hidden sector, and now you put a bulk scalar field, and then you have two localized actions with lambda phi 4. This is the basic setup you originally. Okay? So in addition you have a bulk set. Okay? So with this, what you will have is that you will end up having a vacuum expectation value for phi, but this which will depend upon y, okay? So essentially we have so you want to solve for the phi of y, right? Essentially phi of y. Solution for the phi of y, it will be the same equation as what we wrote for the previous case essentially, except that instead of the mass terms we are writing lambda terms. Instead of the mass terms we are writing for the lambda terms. So you have for the profile which we call it as f of phi or f of phi of phi, because I am using a different notation, or this also can be written in the previous language. This is nothing but f of phi, okay, is equal to minus 1 by r squared del phi e power minus 4 sigma del phi. It's a huge equation, plus m square e power minus 4 sigma phi plus 4 e power minus sigma lambda v phi times phi square minus v square sitting at delta phi minus pi by r, and the same thing also here. So you get an equation, okay. This again essentially you have to have this instead of mass terms, essentially you have complicated data, these things, interaction terms essentially. So you say that this also has some solutions. This has some solutions. Phi of phi is equal to e power 2 sigma a e power mu sigma plus b e power minus mu sigma, where nu is equal to, we call it b in the previous graph, 4 plus m square by k. It's exactly the same thing. It's exactly the same thing as previously. Earlier we call it as a as some constants. Okay, nu m square by c is nothing but b or a m square plus, because m square is nothing but a k square, right? Essentially m square by k is nothing but a. Now what it does is you put this solution back, you put it back into the equation of motions, into the action. Put this solution back into the action. And then integrate over phi, integrate over phi or y essentially. This gives me an effective action essentially. This gives me an effective potential in terms of R. Okay, this gives me an effective potential in terms of R, and and which has to be solved numerically to be exact, but we can take approximations essentially. So the effective potential comes after integrating out over phi. So if you do this integration, the effective action comes out after integration, putting back that solution here into the action. Integrating over phi, this angle, you get v phi over r is equal to k mu plus 2 a square. A is some constant essentially, e power mu k r phi. I'm writing r phi as 1. Problem is I am combining two notations. I was lazy to use the same notation for everything essentially. Now I put back the solution for phi in it, okay, and then integrate of phi. I get phi of 0, okay, phi of the value of the field at 0, value of field at phi, because I have to choose my delta function, and this is just the solutions. I put it back into the potential. Now the basic idea here is that I'll have a minimum of this thing, which is a function of R. Which is a function of R. I'll have a minimum of this. You can solve it numerically and show that R gets minimized essentially. Okay, you are getting a R dependent equation of motion. potential, and the R gets minimum essentially. So you can solve this thing, and in the end, okay, you can show that KR has 4 by pi a minimum is an approximate. Numerical you can do it exactly. K square by m square ln bh by b. So this has a minima. So what you did essentially that you what you did was you put a bulk scalar field with interaction terms, okay, and because of the delta, and you put two boundary localized terms. The moment you put in boundary localized terms, the information of the boundary, okay, at R enters the equations of motion essentially. The R enters the equation of motion. You put it back into the, you assume a solution for this differential equation of the fourth dimension, of the fifth dimension, and you, this solution you put it back into the action, okay, and then you derive an effective potential in terms of R. Effective potential in terms of an R, because you now integrated out phi. Phi is gone, but then R still remains in the equation of motion, in the potential terms. Now you show that there is a minimum for this R value it can take. The minimum the R value can take, which is determined in terms of the interaction strengths. Okay, which is determined in terms of the interaction strengths and the constants you put in at the boundaries, VV and V. What do you call VV and VH? Okay, and m square by k square by m square is the bulk mass term, which is nothing but A, essentially the coefficient. This is order 1. So all of them are order 1, and if you choose this parameter roughly of this thing, if you choose them to be 1 order 10 or something, you should get a number 10 of the order 10 finally, which is very easy to choose essentially. Which is very easy to choose. So this is how you stabilize R, KR close to some 11 or 12 or whatever you want essentially by choosing order 1 numbers. So what exactly is happening here? So what is exactly happening here? Physically, gravity is an attraction force. Gravity is an attractive force, but there should be something which is causing some repulsion, okay, to keep it stable. So in the bulk I have not added any interaction terms. There is no phi-4 theory, nothing. It's just a mass terms essentially. But at the boundaries, I am adding two interaction terms essentially, which are phi-4 like things. These are acting some sort of like repulsive forces. They are acting like repulsive forces. Okay. The scalar field in the bulk with these boundary conditions is acting as a repulsive force, to keep it stable essentially. Okay. Now you can show. So what would be the corrections, small perturbations to this potential? So under small perturbations to this potential also, we can take a small perturbation to this potential, V plus delta V. You can show under delta V also, these corrections are small essentially. You just take stability, do a stability analysis. How do you do a stability analysis? You just perturb all the parameters by a small delta or something, okay, in the potential, and you can show that this is reasonably stable. Okay, we all do stability analysis, no? The same thing essentially. Okay. So this is the famous Goldberger-Weiss mechanism. There are other cosmological solutions also. Okay, there are papers by other people, Steinhardt and everything. who looked at localization of this brains and everything essentially. Okay. So this is how you solve the stabilization problem. So Randall-Sundar model is stable within these distances. The radius can be stable. You can put in zero modes. You can localize them at IR modes. Okay. So we have put so far the scalar field essentially, which is essentially the. Okay. So okay, yeah. So next we have to put in fermions, gauge fields, and then build the entire standard model, the corresponding ones. Okay. I wanted to finish all of that today again, but it's already, yeah. So maybe I won't start fermions now. It will take half an hour more, maybe more actually. So fermions and gauge fields, and then I have do flavor and technical. Okay. I'll do flavor and technical. Okay. And then I don't know. What else you want here other than Randall-Sundar model? Do you want anything else? I think Randall-Sundar will take at least 2 more or 3 lectures. I don't know. If there are anything, then I'll do it in January. Okay. Rest of the things. I mean, we can informally meet. We're always just small bunch. I can tell whoever wants to listen, just send me an email and I'll talk about it. Okay. I think I wanted to talk something more, but yeah.
Can you at some point that two HDA models?
2 HDA models. Oh yeah. You're interested in 2 HDA? Yeah, I can tell you that. All the types, everything. Yeah.